Okay, folks, time for us to get started. We're going to have our next lecture this morning. We're very happy to have Professor Pri Narang from University of California, Los Angeles with us. Pri is actually also a member of the Quantum Science Center, so she represents a lot of the work that we're doing. Today, she'll be talking about quantum matter through the lens of quantum information. So let's give a warm welcome to Professor Narang.
Awesome. Thank you so much for being here. And thank you for the introduction, the opportunity to present some of the work that we're doing. As Travis just mentioned, I'm part of the Quantum Science Center. And a lot of the work I'll talk about here today is actually enabled by the Quantum Science Center. So you'll see that there is a fun intersection from ideas in condensed matter, traditional condensed matter, with ideas that come from theoretical quantum information and how we might be able to actually use quantum devices to learn about condensed matter, right? So normally when you see the words condensed matter and quantum information together, you probably immediately say, oh, cool, yet another talk where somebody's going to tell me that I can predict many-body states using quantum devices. This is the nth talk on that, let me zone out. Do not do that, because that's not what this talk is on. I will try and give you a different lens and a different understanding to think about condensed matter, again, using ideas from quantum information, but also specifically ideas in quantum sensing. So I was told it's fair game. If you want to ask me questions as I go along, just raise your hand. And if I don't see your hand for about 10 seconds or so, start waving, because maybe you're in a blind spot. Okay. So I'll try and cover a whole bunch. I was told I have an hour and 15 minutes, so I understand I will be all that stands between you and lunch. So maybe I'll towards the end start speeding up. I'll tell you first about how we can leverage CQED to both understand and engineer time reversal symmetry breaking. This is a fundamental concept in condensed matter, not just in condensed matter, actually more generally, but really being able to both probe and controllably get into regimes of symmetry broken states is quite important. I will try and convince you that this is actually more general and that we can think about all kinds of non-reciprocity with this idea of quantum geometry. And I'll also link that with noise magnetometry of quantum matter. So essentially where noise can be an advantage for us to understand condensed matter, okay? Then I'll switch gears and tell you about some of the really recent work we're doing that intersects with the first part of the talk. First, in thinking about cavities in a different sense, both to control superconductors and to control topological quantum matter. This is all work that's happened over the last few years in the QSC. So I'm really, really excited to tell you about it. And towards the end, my new obsession, maybe not so new obsession, but just an obsession now, which is axions, both axions in condensed matter and using quantum matter to detect axions. Okay, so it's going to be action-packed. Let's wake up, and hopefully you've had enough coffee first to hear about CQED, right? So how many of you have encountered some of the ideas in circuit QED? Okay, excellent. Okay, even if you haven't, perhaps you've heard about some of the work that's happening in creating and thinking about superconducting devices, and you've heard this word transmon. And don't worry if you haven't heard the word transmon. I'm really going to assume that you understand essentially a classical LC circuit, right? So something that has an inductor, something that has a capacitor. And I was once told if you can understand things through the lens of very, very, very simple LC circuits, life is good. So that's what I will strive to do in the next few minutes here. So essentially what we can think about here is that our fancy superconducting circuitry, the way we would normally describe it using a fairly complex Hamiltonian, in our context, it becomes a really, really, really good sensor, right? So everything that our colleagues are trying to do in superconducting devices, getting rid of all the noise sources, thinking about how things couple to the environment. This is the beauty of quantum sensing. I can turn that all the other way around and say, well, I want that coupling to the environment. I want that coupling in order to be able to sense something very specific. Now, don't get me wrong. I don't want coupling to all degrees of freedom, all parts of the environment. I want our circuit here, our very, very nice a well-designed resonator with an exceptionally high quality factor, great coherence, and controllable properties to couple to quantum matter, okay? So far, I've said nothing about what this quantum matter is. It's just a yellow box. Take it as a yellow box for the next few minutes. what I'm going to do is describe this complex superconducting circuitry using this classical LC circuit model, okay? And the idea would be that in some way, I can relate the properties of this complex quantum matter to the properties of this circuit, right? And at this point, then it won't matter for me if I have a single resonator, perhaps over time I have a series of these resonators, as long as I can, again, start invoking this language of inductance and capacitance. But strictly speaking, it's not completely classical. We're going to think about the quantum inductance and the quantum capacitance associated with this, right? Okay, so how am I going to go ahead and do that? Well, some time ago, folks were able to relate the quantum capacitance to the many-body density of states, right? And the quantum inductance specifically to the superfluid density. And so now you're starting to see that these two concepts are not entirely unrelated. I can essentially say that the many-body density of states, by the way, not to be confused with a single particle density of states. So those of you who don't encounter these in your daily life, just know that getting access to the single particle density of states is a lot easier. Many single particle measurements, including photoemission, are pretty common, but having full access to the many-body density of states is exceptionally hard. Though when we think about some of the topological quantum matter and topological phase transitions, we really ought to know the many-body density of states, okay? So what I can do is relate the quantum capacitance of that circuit that's coupling to the magical yellow box to its many-body density of states. And I can think about the inductance as related to the superfluid density. And superfluid density in particular is exceptionally important here because it's going to tell me, thank you so much, about the symmetry of my superconductor, right? So one of the things, and I brought this up by saying we want access to properties that are related to time reversal, and broken time reversal symmetry is, of course, something that will give me very exciting types of superconductors. Also something that is notoriously hard to characterize, right? So if I think about the ways that I could get access to the same property, particularly in TRSV superconductors, well, that's going to require, some kind of mu-SR measurement, or it's going to require some very, very complex measurement that only exists in 1 or 2 labs around the world. Of course, I say this at Oak Ridge, which is one of the spots where such a measurement would be possible, but most labs would not have access to this. In fact, it's exceptionally hard to get that type of information. So the claim here would be that this boring gold circuit, right, this very, very simple model that we have actually is going to give me access to a lot of properties of this quantum matter that don't necessarily show up all in a single measurement or show up in measurements that you can reliably do in a university lab. And what we'll further explore, of course, is exactly what this coupling looks like. And how do I know that this coupling is giving me access to the information that I claim it is, right? And you can already see where this is going, because as soon as I start to ask, what information am I getting out of this measurement? And I'm talking about a quantum sensor. I can immediately start to talk about the bounds associated with this. I can talk about what is the maximum amount of information I can extract from this measurement. I can start to talk about, am I saturating the Kramer-Rao bound? Very well-defined questions become available as soon as I can frame it in this manner, okay? But I haven't completely done that. So far, I waved my hand. I've said there's an LC circuit. I've said something about the quantum inductance, the capacitance, but I haven't actually kind of closed that loop here. So let me spend the next few minutes doing that, okay? But the heuristic picture will remain the same. I have some form of resonator, this form of superconducting circuitry. It's able to couple to my chunk of quantum matter. Say I have a friend in synthesis who's given me a quantum spin liquid that morning, and I want to know, well, is it a quantum spin liquid or not? So how would I answer that question? Yes? That's right, yes. So those are associated with the quantum matter that is sitting in this circuit. What I haven't so far shown is that that is all you're probing and that everything else is not yet contributing. So that's a valid question. And the other piece of it that I haven't yet shown is, of course, what happens in different regimes of this quantum inductance, right? So if you have, say, a nodal or not a nodal superconductor, what would that look like? If you have something that respects or breaks time reversal symmetry, what would that look like? Yeah. Okay, so if no questions on the heuristic part, let me start diving into more of the details here. And let me start by acknowledging that thinking about the superfluid density and thinking about this picture, taking this idea of quantum inductance is not all that new in itself, okay? Very old measurements, actually measurements going all the way back to Walter Hardy, have talked about how you could do, say, microwave measurements of some well-known superconductors, including the cuprates like YBCO, right? So why am I bringing up microwave measurements? Well, I brought up superconducting circuitry, and that, of course, will leverage some of the microwave electronics that we have access to. That's kind of the whole game that everyone in the field uses. So really, there is a link here that's more than just, okay, we're all looking at just superconductors, okay? But there are some other concepts here, right? So understanding this superfluid density, it's not entirely independent of some knowledge of the superconductor. Typically, you'd say, okay, maybe I have something that's non-monotonic. Maybe I have something that's just a boring S-wave superconductor. Is it a single component or multi-component superconductor? And if you haven't thought about these, and I recognize many of you don't come from a condensed matter background, don't worry about it. These are essentially they're types of superconductors that are in the superconducting phase that are made up of one component, some that have, say, two components, and you essentially think about the relative phase between the two components. When you say that something breaks time reversal symmetry, you'd say that that relative phase is breaking time reversal. So that's really kind of the high-level picture. Beyond that, there's entire semester-long courses that are taught on superconductors. I won't try and compress those here in 5 minutes, but just to say that this behavior should all show up in that quantum inductance, okay? So if I was doing a measurement on this LC circuit and I was somehow very precisely sweeping through a set of frequencies, again, using my microwave electronics, I ought to be able to immediately say, I have something that is S-wave, D-wave, and that, of course, gives me knowledge of the microscopic behavior of the superconductor in a way that I wouldn't normally know, right? So why is this hard, right? You've probably, at least roughly in the news, seen that knowing something about superconductors is hard. It's easy to say I have a superconductor. It's very hard to say what the pairing mechanism is. It's even harder when that pairing mechanism is not boring S-wave, okay? And if it's two-component or if it breaks time reversal, life becomes really, really hard. So the canonical example of this is twisted bilayer graphene. It's a well-studied system. Almost everyone has thought about a twisted bilayer at one point or another. And something that we know is that, yes, it has a nice superconducting phase. What we don't know is what the nature of the pairing interaction there is. So despite thousands of papers, maybe tens of thousands by this point, being written about twisted bilayer, knowing something about the pairing is hard. This is all to say that, yes, some of the papers here go way back. I think this is from the old Russian literature and then reproduced in 2006. So there really is a long history of understanding superconductors, but it's also because it's really, really hard. And I think this is a question that quantum sensing can help with. This is an area where thinking about it through the lens of quantum information, it can give us something that is fundamentally new and has not been explored before, okay? So I keep talking about, this magical quantum matter. Let me put a little more color around it. So it's sitting in the resonator. It's sitting in, say, a specific spot of the resonator. And now you might ask, okay, can you be more specific about this system? So since we're talking about the superfluid density, since we're talking about the inductance, let's just talk about superconductors for a second. It need not be a bulk or just a thin film. It could be, say, a deposited niobium nitride that has a ferromagnet sitting on top. That's something that ought to give you what people call a proximatized region. This is, again, something that the claim would be that we have something that is magnetic. This should allow us to break time reversal symmetry. I should be able to do some measurement on that proximatized region. This is exactly the type of measurement that our resonator would be, or our setup would be pretty good at. We could think about, say, a boring superconductor like aluminum sitting together with a ferromagnet, and then have a slightly more exciting system like graphene, sandwich, and hexagonal boron nitride sitting in the middle. or we could get even more complicated and decide that we want to gate the system. Perhaps this could be tungsten ditelluride, twisted bilayer graphene, or something that involves all of those. So ultimately, we want to know something about what's happening in this resonator that either is associated with the magnetic field map or the electric field map, of course, depending on whether we're looking at the inductance or the capacitance, and then relate that back to a measurement protocol, okay? So I've said a few different words here that hopefully are getting your neural network geared up in the right direction. First is that this is a resonator that I can model using electromagnetics. That is the simple piece of the resonator, okay? That's what the fields are doing. Are they concentrated? Am I accessing this proximatized region or not? What's going on? Then there's a separate piece of this, which is the quantum measurement piece. And I've alluded to it a little bit. And I've also mentioned something here very briefly, that depending on the type of system we're looking at, we could also come up with an optimal measurement protocol, okay? So those are all things that hopefully are reminding you of things that you've heard about in the quantum sensing introduction piece of this. So the quantum capacitance similarly gives us access to interesting properties. And I think to many of us in the room, it's very exciting to be able to look at topological gaps, to look at Chern insulators, quantum spin liquids through the access that we get from these types of circuits and resonators. So the expected sensitivity, if you just look at, say, the electromagnetic response, if you simply look at it through a classical picture, is pretty good. And you can compare that to, say, doing some form of scanning measurement. So you could essentially say it's the same. But that's not how we think about getting maximum information out in a quantum measurement context. And thinking about resolution is not necessarily how we quantify how a quantum measurement is done. So really, we have to come up with different language. We have to come up with a different way of framing this problem. So as we were going through this, we said, well, what would that language be? And how would I go from this general quantum matter, each that has its own type of Hamiltonian, to something that is general enough that I can simply talk about where we are relative to some information theory bound, right? You kind of see the gap. It has all the ingredients. I know there's a quantum measurement. There's some interesting quantum sensing happening. I can see where it goes with the microscopic complexity of all different types of quantum matter. And then there's another direction where I can coarse grain it enough that I see the ability to leverage the quantum information theory language, right? Does everyone kind of see that, and why we're going to try and take a different tack and not get stuck on every single type of system that I could put into this resonator, right? Okay, so to do that and to think about that, we said, okay, let's scrap this idea of looking at every specific type of system sitting in that gap, and let's talk about it very, very generally. And our very general picture here will involve this Hamiltonian, where we have, say, we're describing pseudomagnetic fields and a set of spins, right? So you might say, well, why did we do that? Why did we, go that far? Couldn't we have done slightly better? Well, turns out that I can talk about this circuit. I can talk about the circuit having a set of photon occupation. It's microwaves, but still talk about occupation. And I can relate that occupation directly to a very general property of quantum matter, which is a quantum metric, right? So once I put this complicated type of quantum matter I have on the Bloch sphere, I can really just talk about the distance moved on the Bloch sphere. I can talk about a quantum metric, and that is independent of all of the microscopic complexity that we've been talking about in the last few minutes. So now I have to show you that those two things are equivalent, or at least they're equivalent enough that I can come up with a measurement protocol or an answer from such a picture, and it still represents the more complex picture I just showed you. Okay, so I will come back to this piece of this where I will relate and hopefully by the 11:15 mark have convinced you that this whole thing is really just determined more generally by the susceptibility and conductivity. We don't really need to worry about the specifics of the type of quantum matter, and that's actually a helpful thing for us. But before I do that, let me just say a few things about what this could look like, okay? So we want contactless detection. Why do we want contactless detection? Well, we want to be able to do a measurement on one thing, swap it out, do a measurement on another thing. So hopefully the resonators will allow me to do this, right? The other thing, which is actually pretty profound, is that I can start to map the type of Hamiltonian. I can essentially think of my quantum matter as sitting in this pseudomagnetic field. I can think about a very, very simple spin model for it. And once I map it onto a block sphere and think about this quantum metric, I can also design some form of protocol to maximize the information I'm getting out of it, right? This can be across a wide range of frequencies. So we've envisioned everything so far as sitting in a superconducting circuit in a microwave, but this could all also be equivalently done in on-chip terahertz. And that's something that we and others are working on. And ideally, we'd be able to do this from room temperature down to millikelvin temperatures. Everything for the moment sits at pretty low temperature, but that's not necessarily the case. Okay, so who are the people who've actually done the work? Everything I'm talking about here today is in this paper. This should appear soon. It's the work of Yanis Petridis, who's a postdoc who's worked with me on this, as well as John Curtis. They were both QSC supported. And when they first started working on this topic, okay, a little sidebar. When they started working on this topic, they thought it was insane. They truly thought that this idea that we would take all the microscopics away and be able to write all of this in this kind of general framework was insane. They're like, yeah, sure, we'll do that. Yes, Pri. And it turns out that it's actually not that insane. And the experimental work is all being led by a colleague and friend, Amir Yacobi, as well as his graduate student, Murray Wesson. Okay, so the question was, that picture we have of the resonator, is that this classical electrodynamics kind of picture with the fields, the field intensities? What's that going to look like when I talk about just a single photon occupying this? And then instead of a single resonator, what would happen if I have, say, different resonators, including, say, a cross resonator, right? A cross resonator is actually pretty exciting, or a series of cross resonators, because you would say if I have, say, some phase information, I can actually scan through it. I can essentially think of this as a very fancy interferometry measurement on my quantum matter, right? So I can talk about one arm being populated with a single photon, no photons in any of the others, and I can ask, well, what are the odds that I find a photon in one of the other arms eventually, right? So those types of questions have been asked in a standard quantum sensing context, but we needed to do it slightly differently because, again, remember, we also had to relate it back to this spin sitting in a pseudomagnetic fields picture, okay? But we went through that, and something that we were able to kind of figure out is that you could actually, first with a single resonator and then with a cross resonator, ask what would be the impact of having a photon in there. And you could frame this entire question, particularly for time reversal symmetry breaking, in terms of the reciprocity or the non-reciprocity associated with the response with this resonator, okay? Has everyone heard the word reciprocity in a science context? No, okay, so I see one hand. Thank you. I was waiting for somebody to say, wait, reciprocity, is this like a human reciprocity thing? No, this is electromagnetic reciprocity or non-reciprocity. So essentially, what I can show is that normally if I have photons going one way, they can typically go the other way as well. The medium will allow for that to be the case, okay? But if I apply magnetic fields, frequently what can happen is I can go one way, but not necessarily go the other way. The applied magnetic fields component is the essential piece of non-reciprocity typically, right? This is how we have isolators. This is also how pretty much every bit of telecom technology that you rely on to call your mom works, okay? But that is, if you think about, applying an external magnetic fields, you are breaking time reversal by applying the fields. Now we're asking the question, if you have something that breaks time reversal that's sitting in this resonator, how do the properties of that, the fact that it breaks time reversal, show up in the response of the resonator? Do you see the difference between the two questions? Yes. Yeah, so essentially, you could think of that as a built-in field, so rather than an external magnetic field, right? And so that's this concept that I need to have some way of capturing that broken time reversal but I'm not doing it by taking a giant magnet and using that to break time reversal. I have some property of the material itself that breaks time reversal. So we could think about this also if, for those of you who've taken E&M, through the lens of looking at the epsilon tensor, so looking at the dielectric tensor. If you have both diagonal and off-diagonal terms, and the off-diagonal terms are non-zero, then turns out that you immediately have something that is non-reciprocal, right? And you could characterize non-reciprocity using, and people do that, right? They do that in photonics quite generally. So thinking about non-reciprocity is a well-defined concept. You could talk about even thermal reciprocity or non-reciprocity. So there are some interesting implications of that. In this case, what we're trying to do is take the property of this condensate, take the property of this many-body state, say that how it's being probed in a resonator actually shows up in the reciprocal or non-reciprocal response, okay? So remember, we motivated this thing by saying, how do I know if I have something that breaks time reversal symmetry? I have a quantum spin liquid. I have some time reversal symmetry broken superconductor. How do I know I have that, right? To leading order, what it should do is this global property. It should show up in the measurement that we're coming up with. It doesn't just show up in a passive sense, so that's the hard part. That's where kind of designing this protocol becomes necessary, and also relating it to the quantum metric. Okay, I see. Yes, go ahead. Yes, this is a real experiment. Yeah. So this is all kind of using the transmon circuitry. So this is all in the microwave, essentially. This is not necessarily. So you're thinking of this, through is it in the visible IR? This is all microwave circuitry so far. That's right. Yeah. So we'll talk about the type of detector, because whether you're doing this in this kind of homodiode context, or if you want to do kind of counts and collect statistics, slightly different. And the type of protocol you design for that is slightly different. Yeah. And those measurements are also all being done in Amir's lab. Yeah. Other questions around this. It's super important that at least to leading order, people understand that we're doing some form of interferometry, some form of quantum sensing measurement on this quantum matter, okay? That if you get that part, you're more or less with me so far. Hopefully you've also seen a little more of the subtleties. Yes? Yeah, it's stuff that people have in the transmon world. So essentially, when I say transmon world, I'm really referring to superconducting circuitry that people are using, to build superconducting quantum computers. So yeah, these are elements that look quite different from how you would think about a beam splitter normally, but it's accomplishing the same thing. I don't think I have photos of devices here, but I can pull them up later, and then you'll kind of look at it and say like, yeah. And these resonators, by the way, are surprisingly big, okay? So when you talk about this in the terahertz, you talk about something that's on chip, it's really, really tiny. When you talk about something that's in the microwave, people are talking about like stuff, like the controls are big, the stuff is just big, okay? Which is both good and also a little challenging, because most of the stuff we're trying to characterize is very small. So the largest samples that people want to ship here are about yay large, and the types of things people are patterning are still pretty big. Yeah, okay. But good questions. You're trying to visualize what the measurement looks like. You're trying to think about how you would maybe yourself do it, which is great. That gives me hope that this measurement will become a widely adopted one. Okay, so somebody asked, how do you relate this to kind of all of these properties? Can you talk more about the pseudomagnetic field? And can you really talk about, how all of this kind of shows up in that same quantum metric piece? So let me just tell you that for all linear media, right, this could be whether you're looking at the current or you're expanding out in polarization or magnetization, each of these I can technically access through either thinking about the susceptibility or the conductivity, right? So when I mentioned that we are characterizing all kinds of quantum matter, all I have to do is for kind of the simple SU2 spin sitting in a pseudomagnetic field model, write out what the response would be, what the econometric would be, what the behavior would be. That is actually super general. I could access either the Berry phase of some complicated topological material. I could think about the behavior of certain multiferroic materials. Really, I just need to know what part of these expansions I'm looking at, and it all kind of relates back to that same susceptibility and conductivity response. I can even, through the same lens, actually look at axial electrodynamics, something that I was pretty excited about. I can look at things that are very well characterized, like topological insulators. I can also, of course, I've been talking about superconductors endlessly, so hopefully you can think about that. Okay, so what's going on? Why are all these things equivalent and why, right? So we have some effective magnetic field, and now we want to think about, essentially being able to scan in some kind of frequency band. This is essentially thinking about these SU2 spins sitting in a magnetic field. I can map them onto a Bloch sphere. Everyone seen a Bloch sphere? Okay, great. I was, week 2 of an NQI summer school, you have to have seen a Bloch sphere. Probably you're sick of seeing a Bloch sphere by now. Maybe you have dreams about the Bloch sphere. But the key thing is that on this Bloch sphere, I can actually map, so all of these complicated states, right? And this complicated description, now I can really just capture it as a spin sitting on this sphere. And what I'm talking about is that as I go through some set of operations, I move on the sphere, and those operations are not just going to be random. Those operations are going to be very well defined, and they'll give me access to the econometric, okay? So this idea of not just randomly moving around the Bloch sphere, but actually doing well-defined operations is called process tomography. This is something that you could think about. People think about process tomography regardless of the types of measurements I'm talking about. It's a very general field. It's I'm not doing it justice in my 30 seconds of description here, but it's actually pretty profound in order to actually do different kinds of kind of measurements. Okay, so we now needed to think about, okay, how am I going to, with this cross resonator, this maximum amount of complexity that I have already engineered into the system, get a well-defined response about my type of quantum matter, right? Okay, so first, we are operating with a Y gate, and this is what you would refer to as the forward geometry. Okay, all good. Then we go through some time evolution. Okay, that's also hopefully well understood. Then I do the reverse, which is the backward geometry, and then eventually do some form of measurement. Okay, and at the end of all of that, I've moved some amount on this sphere, and that's the econometric. Okay, now the hard part here is realizing that this econometric has all of the information that I'm interested in about the type of quantum matter that I've been talking about for some time. So all of those weird things on the previous slide, right, written out in their expansion associated with polarization or magnetization, essentially all show up in just this small distance measure. And that's kind of the beauty of this whole thing, because it would not work if that were not the case. And this is, I think, key to this being a protocol. Okay, so we put this out, and those of you who are interested, there's pieces of this that are already in the paper. We also hold some IP on this, and there's a subsequent set of papers on this that are coming out. So I encourage you to keep an eye out for these. There is a related set of work that I will not have the opportunity to talk about in any detail, but I want to mention it, which is where folks are thinking about other kinds of optical measurements that you could do, more conventional optical measurements, where you try and maximize the quantum Fisher information that you can extract out as a measurement. Okay, those are leveraging cavities, not circuit QED, but that's this neither here nor there in terms of the complexity of the measurement itself. So this idea, I think, is going to catch on. I think that for folks who are thinking about how to characterize condensed matter, how to think about it through the lens of quantum information, this could be a fun area to work on. Okay, So now everything was a cross resonator. You might have said, why cross resonator? Well, because I can do, arms interferometry. That was kind of the picture. But if I have a two-component superconductor, right, it seems more natural to now instead do a ring resonator. Why? Because I could think about the angular momentum associated with going clockwise, counterclockwise. I almost forgot which one would switch. Okay. So, if I think about ring resonators, I have, angular momentum modes, propagating, counterpropagating. And these ought to be able to both support and probe multi-component superconducting states that have non-zero angular momentum. Those are the types of superconducting states, types of superconductors that are the hardest to characterize. And you would say, I could think about a resonator like this, perhaps instead of now thinking about just a single photon and an arm, I could think about a standing mode sitting in this, and I could do some kind of power-dependent response as well. Yes? Exactly. Yeah. So it could be, something as exotic as P plus IP, which everyone's looking for, hoping to find. It could be multi-component where there's no relative phase that itself breaks time reversal. So it could be, all of those. Is that a hand or no? Just a head scratch. Okay. So there's also the additional component here that you can couple to those different propagating or counter-propagating modes, and that might give you access to symmetry classes and being able to distinguish these symmetry classes in a way that you may not be able to strictly using the interferometry idea that I've talked about so far. By the way, this has some analogy with high energy physics, and I feel like Oak Ridge is the right place to talk about it, where you can think about, either the oscillations of the outer core of neutron star or proton-neutron instabilities. It's kind of the condensed matter version of that, where these multi-component superconductors couple to different propagating and counter-propagating modes. And we think that that analogy could go even further. So we're building on this idea and hope to put out a paper on this sometime this summer. Yeah, still this summer, yes. Okay. So then the natural question, the natural quantum information question, why stop at one resonator? Why, if you can do state preparation, if you can think about all these protocols for a single resonator, why not do a whole bunch of them? And if you can do a whole bunch of them, why not think about preparing a very specific type of state to probe exactly what you want in this type of quantum matter? So now move away from the generality of any quantum matter somebody synthesized that morning and gave you to say, what is the best possible measurement I can do? What is the way that I could saturate the Kramer-Rao bound? How can I show, right? And what does that mean in this condensed matter context to go beyond the standard quantum limit, right? So hopefully folks saw the SQL introduced earlier in this school. Yes? Sort of? Okay. Well, so we can talk about, where you would be if you were working with a quantum state versus where you were perhaps working with entanglement as a resource in order to do some kind of measurement. And there are different ways that we could talk about that bound. What's not easy is to translate all of that to the type of measurements we're talking about with condensed matter, okay? So what we tried to do is now say, let's be even simpler, right? Before we worry about some very complex entangled state that we're working with to then probe our quantum matter. Let's do just a Fock state or a coherent state, which strictly speaking is still classical, and figure out what type of optimal protocol you could construct here. And we think of this now essentially as a variational circuit, and it essentially can serve as doing some kind of optimal quantum control on this quantum matter. Okay, so you could even program it, we think, to either break or respect time reversal symmetry if you want it through this type of scheme. Is everyone following this? We've made like 4 or 5 different jumps here, so I can briefly summarize those jumps, okay? We had complicated condensed matter. Boring resonator has been around since many of you were, actually since well before many of you were born, okay? That idea of superconducting circuitry, right? We applied it to a very complicated problem. immediately realized that the mathematical language you wanted there was not classical electromagnetics, but you wanted the language of quantum information. We went that route, took a little bit to kind of do this song and dance with the quantum metric, okay? Once we got through that piece of song and dance, we realized, oh gosh, there's this whole set of things that opens up, including optimal measurements, thinking about types of circuits, thinking about types of resonators, bounds, which bounds, what types of states you prepare, how you measure, and all of that good stuff. So those are kind of the steps we've taken so far. Everyone with me? Yes. Right. Okay, this is a hard question. And I'm still on my, I'm sorry? Yeah, so the question was, from some of the lectures, which I wasn't there for last week, that talked about mapping condensed matter onto certain types of error correcting codes and types of quantum devices, if some of that could be useful, or if the way we're thinking about condensed matter and quantum sensing now, what's the connection, okay? And I said this is a hard question because the language is the same, the math is the same, but drawing a direct line or figuring out which way the arrow points is not obvious to me. And here's why, right? Here, we're not really mapping things onto, I use the word mapping to talk about the Bloch sphere, but really what we're doing is we're probing that condensed matter through this type of quantum sensor. And we're asking about measurement. My understanding from, again, not having been at the lectures last week, is that there's more of a mathematical connection and a mapping that's being explored to do better codes or use the codes to better understand many-body states. So the objective ultimately will still be the same, right? How do we understand condensed matter better? Here, it's more of a direct characterization piece, and then figuring out where information theory helps us understand where we are relative to how much we could know. Does that help? Yeah, okay. Yeah. Yeah.
And when they talk about the quantum metric there, it's like a very abstract thing.
Right.
Kind of like, I feel like it seems maybe really powerful. Like if you could, is it the same?
This is the same quantum metric. Yes, this is the same quantum metric. That's right. That's right. Yeah. Thank you. I think that is the first time somebody said that to me during a talk. Thank you. Go ahead. I think this is just supposed to show that you could kind of do a bunch of these resonators. This itself is not supposed to be, what the circuit would look like. And just to kind of put this measurement and its complexity in perspective, the experimentalists and we've all been working on this for several years now. And I don't think it's for lack of trying to kind of get this measurement to be as general as we want. And that's with a single kind of cross resonator scenario. So we're a little ways out from doing this type of, many circuits and optimal control experimentally. But I think it's important to think about that theoretically now, because maybe there's a realization of the circuit that doesn't involve the type of experiments that we're doing. Maybe there's the type of experiment that some of you are doing that could realize this. Yes. Could you speak up a little bit? Sorry. Right. Yeah, so far we've looked at very simple Fock states. That was just our first attempt. You could prepare many more complicated states, right? You could think about GHZ, you could think about types of cluster states. You could use those to then try and understand condensed matter. I know people are working very hard to create these states and to use them, and we and others have done that to kind of characterize molecular systems to characterize confined systems. Nobody's really using that to think about complex condensed matter. That would literally be taking a tensor product of two hard problems. But we are hoping that's slowly starting with the simple states you can create, figuring out what's associated with these types of condensed matter could actually be valuable. So despite the fact that this is all in the realm of quantum science, I'd say there's historically been a pretty big gap between how folks in condensed matter characterize some of these states and how folks in quantum information think about them. So, if I went to a conventional, say, person working on superconductors, somebody, from the Cooperate community, and said, I'm going to now describe it all using this quantum metric, and I'm going to say something about this entire body of literature that goes well, way, way, way back. This is not an easy barrier to overcome. So we have to convince a lot of people that very simple stuff that was known about some of these states, when you do these kinds of measurements, is in fact recovering the types of things they know, before we kind of get into the realm of, preparing a very complex quantum state, using that to study a very complex type of condensed matter. But yeah, we're making strides towards it. And I appreciate the enthusiasm in the audience to try the hardest possible thing, because that means it might actually get done. Yes. So yeah, in this case, it would just be, okay, you could think about just a simple coherent state. Don't worry about a Fock state at the moment. And this is just something that you'd be able to easily prepare in this microwave circuit type of scenario. Yeah, you could do a lot more if we weren't working with these types of superconducting circuits, if you're working with other kinds of quantum sensors. But this is kind of easy enough for now. Yes, that would be yet another kind of avenue to explore, to say that how much can we get out of state preparation and the types of state preparation we do, right? So when we think about quantum measurement, there's how do I look at the more complicated thing? How do I start with the most complex state? And then, how do I do the best possible measurement? And ideally, optimal would really mean all three optimized, applied to a problem of interest. But we're a little ways away from that. Yeah. Yes.
These seems extremely neat, but on the other hand, what I see is that you will have difficulties to make the whole work. So the type of errors will be also more complicated than.
Yeah, for sure.
Have you thought about
how we would. So I would say, for the types of measurements that we're doing, or the types of information we're looking for, getting a very, very high Q resonator with reasonable coherence times is sufficient, because ultimately we do want some coupling to our quantum matter. So we are not at the moment at all limited by the noise that's being introduced by a crappy resonator. Just in terms of the sensitivity, we're so far away from that if somebody gave us an old used resonator, we would probably still be able to do more with that than we can with without using quantum sensors. So I think there's a big kind of gap between where people doing compute need to be and where doing sensing is at. So yeah, I would love to be at a point where we need better resonators for measurements. That would make me very happy. But yeah. Okay, so I want to just also acknowledge that some of the work being done on these geometries is being done by Anastasia Pippi. So if you see papers out from these folks, you'll know what we're talking about. I've already talked about this, so I'll not dwell on this and spend the next few minutes telling you about something that is related, but now taking a different view. So far, we've done direct measurement of quantum matter. Now we're going to think about the noise spectrum, right? So this is just alluded to, that there'll be some noise, and can we actually use that to learn something about our system? And the answer is yes. In fact, we're not the first to say that. So now instead of thinking about superconducting circuits, by the way, you ought to be thinking about, say, a color center that is in diamond, so a small defect that lives in diamond. Has everyone seen color centers? Were these talked about in any of the other talks? Yes? Okay. Perfect. Okay, I see some hands, so hopefully that means people roughly remember. So now you would say, okay, so now what is this color center doing? Well, it's a very, very portable, nice sensor. It can move around. I can move it around a sample. I can use that to do some kind of mapping on our system. And so it's going to pick up the magnetic fluctuations, right? So this sensor moving around, will look at local magnetic fields. And that's something that we and others have done in the past, right? So you could think about doing direct magnetometry. If you did direct magnetometry, as has been done in the past, you could reconstruct the current profile, you could construct what the spins are doing, you could do all kinds of different direct measurements. Something else you could do is now say that there's a noise spectrum associated with this measurement, and what can I learn from that noise spectrum, right? So everyone familiar with this idea that noise is not just flat, there's some spectrum associated with it? Yes, yes. Sure, so it's a defect in diamond. It's what gives, if you've seen fancy diamonds in photos, it's what gives it color. That's why people refer to it as a color center. But really what it is an inclusion in diamond. It's something that is then very sensitive to local magnetic fields. The most common one is a nitrogen vacancy center in diamond, which is literally just a vacancy. And what that gives you access to is essentially, I'd say, it's like something that you could use to do local measurements that look very similar to STM, scanning tunneling microscopy, but you're not actually touching anything. You're just scanning this thing around, and it's giving you kind of what the changes in the local magnetic fields are. Does that make sense? Yes. There's a dye vacancy in diamond that gets a nitrogen. You could also have, it doesn't just have to be nitrogen, you could get silicon, germanium, tin. It can have different charge states, depending on whether the charge state, you could think of it as spin zero or not. There's different color centers. There's like a whole literature of types of color centers. Actually, the very last time I was at Oak Ridge, I gave a talk on color centers in both diamond and 2D materials. I was just thinking as I was saying these words that I've done that exactly in this room. But I can point you to some of that. What's important is that people are thinking of this as kind of a way of doing sensing, and it's become actually a technology. So this type of stuff you can buy. There's a company that can sell NVs sitting on an AFM tip. You can essentially set up this measurement in your lab if you wanted. I forget the name of the company, but yeah, I can share that with you if you're setting up your lab. Yeah. Okay, but rather than thinking about direct measurement, now you could say there's a noise spectrum, and I could do noise magnetometry, and that should actually help. Why should that help? Well, I still retain the resolution that I would have from normal magnetometry. All the advantages are still there, but now I have an additional kind of control knob here. And this is essentially controlled by where this color center sits relative to, say, some 2D material. And I can be very sensitive because, of course, this momentum piece here will be controlled by the distance between my qubit or quantum sensor, depending on what you want to call it, color center. And I can also be very sensitive to types of structure factor. So why would I care? Well, there's a phase transition that people have been trying to characterize for some time, which is the Brzezinski-Kosterlitz-Tallis transition. So BKT physics is something that lots of people care about. And the idea was, well, can we actually look at this noise magnetometry as a probe of the topological BKT transition? Okay. And the short answer is yes. The long answer is it's hard, but doable. Okay. So let me tell you why yes. Well, if you kind of think about the Mervin-Wagner theorem, for D equals 2 and SO2, yes, you can look for this transition. So it is allowed, okay? This is a question people get stuck on a lot. Is this actually mathematically allowed transition? Are you making this up? No, we're not making this up. Turns out it is allowed. And what we predict here is that you actually should be able to see it directly in the Doi spectrum. So this prediction is also out there. And if you're interested in doing this measurement, please contact me. I've been trying to convince a couple of people to do this measurement on my favorite systems, and it's proven to be harder than I'd like. Okay, so we have about 15 minutes, and for the remainder of the time, I'd like to tell you about some of the work we're doing in cavities and thinking about axions. But before that, I want to see if there are any questions on the quantum sensing piece of this. Yes. Yes, it is the same thing. Yeah. Other thoughts, questions? Yes. Sensitivity, I think, is it's a subtle signature. This is something that people forget about topology. It's mathematically very pronounced, but physically something that requires a subtle measurement. So it wouldn't necessarily show up in ODMR, right? It's not something that, at least I would not see how it would be sensitive to looking for a topological phase transition. Were you going somewhere with that question? Maybe I missed more context could help. Of the type of measurement that we're doing? Yeah, so, one of the ones that comes up a lot, right? So if you have, this is a view of what this measurement looks like, right? But typically what would happen is that, of course, this could couple to what you're actually interested in. It would also couple to some other crud that's sitting on the surface. Like I said, we're very sensitive to how far it is from the surface. And lots of things get on surfaces, right? Like water gets on surfaces. It sticks there. It messes with that signature. So we have to be very careful that the noise that we are attributing to our transition is actually our transition, not some other thing that's happening. And so you could kind of think about a temperature sweep. That should help, because not everything has a temperature signature, right? You could think about just kind of being able to map that parameter space so that you know exactly what that transition is doing relative to all the other things. Yeah. Other questions? Yes. For the circuits that I showed you, why don't I answer that question in the break? Because we went through a fair bit of stuff there. It's mostly unpublished work, so I don't want to have that. I don't want to get scooped. I'll say I'm a small team of people working on it. So, but I can answer questions of that during the break. Yeah. Other questions on the quantum sensing piece before I launch into cavities? Is that a hand? No, just a head scratch. Okay, no problem. Okay, so we've talked about resonators, and it's very natural to now ask the question, well, you're probing all these states. How about controlling them, right? And we can control all kinds of excitations in condensed matter. So before I start talking about which types of excitations we are most interested in, I want to just point out that when you think about types of condensed matter, there are collective excitations that you can access. You can optically access many of these collective excitations. These could be things like magnons, essentially a collection of spins. Could be things like plasmons, essentially a bunch of electrons doing a dance. It could be excitons, bound electron hole pairs. You can move those around. It could be some combination of those. It could be the lattice that then couples to light, so phonon polaritons. There's just a whole host of these types of polaritons. In fact, somebody put together a review that talked about the zoo of polaritons that are accessible. And I think there was something like 200 plus, okay? So I give you 4 examples. So what we start to ask is, so you have a resonator, you have a cavity, how does it couple to this collective excitation? And if it were coupling to this collective excitation, could you completely modify behavior of the type of condensed matter you have, okay? So there are ways that you could modify condensed matter, right? You could shine light on it. That's what we do in other contexts. Very often it just melts the thing, but ever so often it creates something new. You could change the temperature. That just moves you through a phase transition. You could strain it. You could literally pull on it or push on it. That can change the type of phase you have. You could just make a different thing. You could dope it. You could electrically bias it. Or my personal favorite, you could think about how it couples to a cavity, right? And in our context, we're going to think about cavities that live in this quantum domain. So we would have the opportunity to control not just, say, a surface excitation or a propagating thing like a plasmon, but actually think about controlling the bulk of condensed matter, okay? So there is a small crew of people out there saying, okay, this cavity, if it's very, very high quality factor, it can couple to excitons. If it couples to an exciton, maybe I can use that to couple to a interesting topological material that hosts these excitons. If you take, say, a certain chain of thought, and this might only make sense to condensed matter folks in the audience, but bear with me, that there are preformed pairs in the pseudogap phase. You could say that a cavity could perhaps couple to these and give you the long-range interaction you need in order to, say, engineer the pairing interaction to create a superconductor or change the transition temperature of it. You could think about coupling to magnons, so spin excitations. And if you couple to those magnons, you could argue that you have the ability to use a cavity to change the magnetic properties of this material, right? So all of this relies on some way that the cavity actually couples. And we recently started thinking about how the cavity could couple to this very, very fun, complex system, manganese bismuth telluride, MBT. It's believed to be an axion insulator. I say the word believe because depending on who you ask, it has either been rigorously shown to be an axion insulator or is on its way to being shown to be an axion insulator. Regardless of where you fall on that, it has interesting phonons as well as magnons that you can couple to. And the idea would be that you use the cavity to couple to these in order to actually take it through that magnetotopological transition, okay? So essentially, you're using the cavity to drive it through the transition. Everything we've done so far, we've used our knowledge of quantum mechanics, we've used our knowledge of quantum information to detect a transition, to say something about the type of transition we have. But this is now saying that we could actually use it to drive it through a transition. And this is something we and others are working on. This is a frontier area. How do you use cavities to drive materials through different types of phase transitions, particularly topological phase transitions? So I'm just giving you now what I would call a bird's eye view overview. This is not the level of detail we talked about in the last hour or so, but just to kind of get you thinking where the field is going and perhaps where you might contribute. So the same way that you could think about a topological or magnetotopological transition, you could also think about the cavity actually moving charge density waves around. These are essentially collective excitations that show up in certain types of materials that might undergo ordering. So they could go undergo charge or spin ordering. You could get a charge density wave or spin density wave. And you could think about the cavity actually being able to move such density waves around. Depinning CDWs is actually pretty important because frequently getting a charge density wave competes with having a superconducting phase. So folks would say that if you can kind of depin or you can use the cavity to prevent the CDW, then you might be able to actually make it a superconductor in regimes where it would not be a superconductor. So again, this is something that we others are thinking about. If you have ideas on it, I'm very open to it. And of course, there is the direct kind of coupling to a superconductor. This is something that John Curtis and several of the people in my group have been now thinking about for some time. Question is, if you have several quasi-particles, and this makes a lot of sense if you have a flat band superconductor, please don't worry at this point whether it breaks or doesn't break time reversal symmetry. That's a level of complexity we should not get into for cavity control. But what we've been thinking about is actually how you might tailor the parameter space your superconductor can live in and use the cavity to control it. And this would be, again, through controlling these optical transitions of these pairs that exist. So these are, say, some of the ideas where we have quantum optics. That's kind of the types of cavities we're talking about, condensed matter, and some ideas from quantum information that are entering. Okay. I think I'm out of time here almost. So I'll just skip through this. And I don't know why I thought this could all be covered in an hour and 15 minutes. I was very optimistic. I have 5 minutes. Yeah, I'll wrap. I just, there's no, somehow I thought I had like an hour and a half, or maybe I just assumed I would talk fast. Not enough coffee. Okay. So I've tried to convince you that, there are various fields of quantum information that are all coming together. And I think this idea of how do we think about condensed matter through the lens of quantum information, particularly information theory, is new. It's something that I hope will catch on, and hopefully something that you would be interested in working on. The simplest example of that I showed you today is CQED and time reversal symmetry breaking, but give you an idea of where that could go more broadly. I think noise magnetometry is another avenue where quantum sensing and condensed matter intersect. This is something that this intersection has already started to reveal some interesting features. And I think that plus how we think about topological phase transitions is going to be even better. And then I think that if you believe all of that, and you say, okay, this quantum information condensed matter angle is fun, then I'd say add an additional piece to it and talk about cavity control. And then you really have access to a much broader parameter space. So with that, I want to thank you for your attention. Take any more questions. And I am around today, tomorrow, and part of Wednesday. So you can ask me about the Axion stuff that I didn't talk about. You're also welcome to ask me about some of the unpublished work that I alluded to but didn't want to show you here today. And thank you for your attention.
Okay, we'll take time for a few questions.
So thank you for your talk. So can you explain me the last slide you showed for the non-equilibrium quasi-particles? So there are two figures. Can you
Sure.
explain them to me?
Okay. Opportunity to go back and talk more. Love it. Okay. Here or here?
The previous one probably. Yeah, this one.
Okay.
So
yeah, so the idea is that, if you think about, say there's some thermal distribution of these quasi-particles that the cavity is coupling to, the claim would be that the cavity is selectively coupling to certain energy bands, right? Because you can pick what kind of cavity you have, and you're moving that population around. So you're going from a thermal population of those quasi-particles to a non-equilibrium version by essentially using the cavity, coupling them, and moving them. So that's the essence of the idea. And since you ask, and since there is maybe 10 seconds, I'll say that you could actually, in the near field, drive these types of thermal quasi-particles, right? So once you couple to them, you've selected them out, right? So that's kind of the picture I have. You can now start, in the near field, at least driving these. And that would look like essentially optical control of this flat band superconductor. This should be relevant even for things where the pairing is not known, like twisted bilayer, but also, other kinds of flat band superconductors that have been reported in the past few years. Yeah.
Other questions? Okay, not seeing any. Let's thank our speaker one last time.